up a week from now in the middle of the night, if you suddenly wake up a week from now in the middle of the night and you have a question that you didn't remember to ask tonight, you're certainly welcome to send me an email. I will do my best to help you find an answer or give you something to read or new YouTube videos to go watch or something like that. That's my blog there right underneath my email address. I write for the public. It's been kind of slow since the pandemic started, but I'm trying to get back into the groove there and start posting again. But it's meant for the public. As I like to tell people, it's there so my folks know what sorts of things that I work on. My folks are both foresters and biologists, botanists. So I talk about all kinds of different things in astronomy, lots of the things that you'll hear about here tonight. There's my social media contacts if you want to follow me on social media. So this image in the background is a very beautiful, what we call barred spiral galaxy, which you can see in the constellation Eridanus. This is NGC 1300. You can see it in an amateur telescope, and in a larger amateur telescope, you can certainly see the spiral structures in the galaxy when you look at it. That is something that even just 100 years ago for professionals was not really that possible. 100 years ago, professionals were still arguing about what the nature of galaxies were. And when you look at this image, if you've looked at galaxies a lot, and you've certainly taken astronomy, you have learned enough to recognize that you can see in this spiral galaxy that it is formed of stars, that there are brighter, bluer regions, which are star-forming regions that have strewn themselves out in these very elegant spiral arms that stretch around the galaxy. That's a discovery. That's something that we understand about galaxies that has been around for less than a century, which is less than the life of people that you may know. And that was really the inspiring thought for when I first sat down and thought about writing this talk is, wow, it's remarkable that something we take for granted in the days of my grandmother, they just didn't even know was true. Okay, so that's the whole premise here. And the common thread through this entire talk is that our ability to discover all the things that I'm about to tell you about is because our technology has been improving, especially in the last century, by leaps and bounds. And it is poised to still continue over the next century. And we'll talk a little bit about that. So the beginning point is that the universe is really old, and we know it's really old. It's 14.6 billion years old, and it is enormous and vast beyond the ability for our tiny human minds to comprehend. But there are plenty of mysteries and plenty of neat things that we are still discovering today, precisely because it is so old and it is so vast. And all of the things that were mysteries long ago that we've now resolved are a consequence of our ability to probe this immense volume and this immense age that the universe really has. The career as an astronomer, whether you're a professional or an amateur, is really very short. Being conservative, it might only be 5 decades long, 50 years. So I'm 50 now, and I picked up a telescope when I was, 5 years old or something like that. The first time my mom gave me her Birders spotting scope. So my career at this point is 50 years. So that's why that's a conservative estimate. I imagine I'm still going to be doing astronomy and still tromping out to the observatory in the backyard 30 years from now. So 50 years is conservative, but as a base estimate, that's a kind of a good number to keep in your head. And then lastly, this is the question, right? This is what we want to understand tonight. How much in just that short 50 years, and actually now that I think about the title, it should have been 60 years, but in that short time, how much can our understanding of the universe change? Okay, and the answer is tremendously, by an awful lot. Okay, so let's dial the Wayback Machine. Let's go back 30 years ago to 1991. So I got my bachelor's degree in physics in 1991. I'm an Oregon State University graduate. And then I went to graduate school. So this is what the universe was like at the beginning of my career as a professional astronomer. I was already an amateur astronomer by then, but at the beginning of my career as a professional astronomer, what was the universe like? Okay. Well, in 1991, the Earth and the other planets in the solar system were the only planets we knew about in the entire universe. Now, we have long suspected and known that there are planets, no, sorry, not known, suspected that there are planets in elsewhere in the universe. Star Wars and Star Trek and all the great science fiction for ages has promised us that there were planets around other stars in the galaxy. But speculating is not the same as knowing, not the same as scientific knowing. And this is really the point. At the time I started my career, just 3 decades ago, within the lifetime of many of you listening, we didn't know with scientific certainty that there were indeed planets around other stars. The solar system was it. Now, some of you are as old as me and will remember that at that time, Pluto was still rightfully a planet. So at that time, we would have said there are 9 known planets in the galaxy, and they are the 9 planets that orbit our entire sun. Okay. In those days, the largest telescope in the world in 1991 was the 5-meter or the 200-inch Hale telescope on Mount Palomar. So it had been built in 1948, and it would be the largest telescope until 1993. So for many, many decades, this was the best, largest instrument that astronomers have to study the universe. And if you go back to Sky and Telescope from the early 90s, you go back to astronomy textbooks from the early 90s, no telescope bigger than this existed. And everything that we knew was discovered with the Hale or smaller. Okay, the Hale, I will say, or remind you, is still in operation. It is still doing science. It observes nightly. I've had the opportunity to do observing runs on the Hale. We do lots of spectroscopy work with it. We follow up on observations by smaller telescopes. It's still a major astronomical instrument in the professional astronomy community. Now, in 1991, the Hubble Space Telescope was brand new. It had launched the previous year in 1990, and those of you who remember that era will remember that it launched with much fanfare from the space shuttle, but it was almost immediately discovered that there was a flaw in the primary mirror. And much has been written about that flaw and the reasons for it and everything that panned up after it. But astronomers very quickly learned how to harness the power of computers to do some digital correcting on the images. And Hubble began returning great science right away, even with its flawed mirror, until the corrective optics, the so-called COSTAR system, was installed by a later Hubble servicing mission on Hubble. Hubble is still active today, so it is 30 years later. It is the longest running space telescope in orbit, and arguably it is the most influential astronomical instrument in the history of the human race. More than 10,000 papers, scientific papers, have been written about the discoveries made with Hubble. It is kind of a mainstay of everything that we do in professional astronomy. It is imbued in the public consciousness. Virtually everyone has heard of Hubble, and if they've seen astronomical images, they have seen images taken by Hubble. It has very much become part of both the scientific landscape, but also our culture in modern society today. So it will be a sad day when we finally lose Hubble, but as part of the discussion today, we're going to talk a little bit about what's going to come after Hubble for when it is no longer with us. I will also say that at this time there was a revolution in amateur astronomy. So the Dobsonian telescope had been around for a while, but I would say right around the time I was in graduate school was when they were first really becoming prominent. You'd start going to star parties and you were starting to see more Dobsonian telescopes than you saw of tripod mounted or German equatorial mounted telescopes. Telescopes were getting bigger for amateurs because of the technology, because of the ability that the Dobsonian technology enabled to carry big, big mirrors. And that's a trend that has continued today. But this was the beginning roughly for amateur astronomy for when this really became very common. Okay, and so these are the classic old style solid tube Dobsonians. You still see some of these around. Many of us still build these. And many of them, as you can see, like this wood one here on the right, are certainly quite beautiful. Okay, so they were solid tubes. And as many of you probably know, today, the technology of this has evolved even further. At that time, the most distant object known to the human race was a quasar. Those of you who have studied cosmology know that we often refer to distances in terms of a number that we call redshift that corresponds to distance via something called the Hubble law. So this was at a redshift of 4.5, which translated into distance is 12.4 billion light years away. So this is called a quasar. Quasar is a shortening of quasi-stellar object. And as the arrow right there is pointing at it, it is just a point of light. And at that time, it was never seen as anything other than just a point of light in a telescope. Okay, and so we didn't know what they were. They were quasi-stellar. Why were they quasi? Because at the distances that they were at, for them to be bright enough to be seen in a telescope, we knew the energy output had to be enormous. Okay, and if I gave you a physics homework problem to calculate how much energy is being output, what we discovered very rapidly is that the quasars were the most energetic objects known to any branch of astronomical science. They just tremendous amounts of energy. It was measurable, but we had no idea where all of that power was coming from. This was the great mystery at the time that I started graduate school. Okay. The last known supernova in the Milky Way in 1991 was Kepler's supernova in 1604. Those of you who know your astronomy history will note that that is 6 years before Galileo first turned a telescope to the skies. So the last supernova in the Milky Way was before the invention of the telescope. Now, this fact is killing astronomers because we would love to see a supernova up close, for reasons we'll discuss in a few moments. And there has not, since the invention of the telescope, let alone in the modern era, been a supernova, despite the fact that galaxies like the Milky Way are supposed to, on average, produce one supernova every 50 years or so. So the Milky Way, by all statistical counting, is long overdue for a supernova. And the last one was in 1604. But astronomy is always on the move, and the frontier was changing right before the 1991 year that we're talking about. So on the 23rd of February, 1987, there was a supernova very close by that we could see. It was not in the Milky Way. It was in a small satellite galaxy of the Milky Way called the Large Magellanic Cloud. And so this set of panels here shows a deep sky picture of the Magellanic Cloud. On the right, the white arrow is pointing not at that big star, but at that little tiny star next to it. That is the star that, when it exploded, became the supernova that you can see there on the left. This is bright enough to see by the naked eye, but it was not as bright as the reports of supernovas in the Milky Way close by are. Supernovas in the Milky Way are bright enough to read by at night. You can see them during the daytime. This was not that bright because it's much farther away, but nonetheless, it is the closest supernova that astronomers have ever had the opportunity to observe. And so all kinds of telescopes just spent years, still today, we spend years looking at the remnants from this supernova when this star exploded, including Hubble. And there's a tremendous amount of science, and we could spend a whole talk talking about supernova 1987A. Okay, but why do we care about supernovas? Well, stars, like people, they live, they're born, they evolve, and eventually they die. And when they die via this explosive process called the supernova. But what they do is they take everything that they have done over the course of their lives, which is turn hydrogen into other stuff, and they throw it out into the universe. And all of that stuff in the universe that the supernova spread around becomes the stuff that you and I are familiar with, whether it's planets, it's rocks, it's kangaroos, it's trees, cheeseburgers, iPhones, Yugos, Lego bricks. Everything that you've ever heard of is made of atoms that have been created during the life and deaths of stars. And supernovas are one of the primary mechanisms by which those materials, the elements that make up all the things that you know and love, are spread around the universe. And so we very intensely want to study one of these supernovas up close to understand exactly what that process of creation of the elements is. This is the origin of the phrase that we are all created from stardust. which Sagan has popularized long ago, and many of us have repeated many times since then. Now, the reason I'm telling you this story about supernova 1987A is because this was the beginning of something that we call precision astronomy. One of the things that we had long suspected should happen when a supernova goes off is all of the atoms in the supernova are broken apart, and the pieces of the atoms, in particular the protons and the electrons, are forced together and they combine to form a neutral particle called a neutron. That's also a part of atoms. But then they also produce a little small particle called a neutrino, that little orange guy up there in the upper right. Neutrinos are something that we discovered less than 100 years ago, but once we knew they existed, we have long suspected that supernovas should produce them in copious amounts. And so one of the ways to study supernovas is not just with an ordinary telescope, taking pictures of it or spectra of it by pointing a telescope at it, but you could study supernovas if you could detect these little tiny particles that we call neutrinos. And as it turns out, when supernova 1987A went off, we had a neutrino detector, several neutrino detectors around the world active. So this is a picture of the most famous of them called Kamiokanda. It's in a mine in Japan. It's basically an enormous water bottle. It's full of water. You can see the scientists there riding around in a rubber raft. And what they're inspecting are cameras. There are thousands and thousands and thousands and thousands of cameras looking at the inside of this enormous jar of water. And what happens is when this neutrino goes through this water, it sometimes interacts with the water and generates a little flash of light, which the cameras detect, and we know a neutrino went through. So when supernova 1987A went off, we detected 24 neutrinos in Kamiokanda and the other observatories around the world. Okay, now that's out of 10 to the 57 neutrinos that were generated by the supernova. Okay, and so this is us learning how to do astronomy without light. That's the message here. So what does that mean? 24 neutrinos after a 1 followed by 57 zeros. Okay, this is an enormous number. Most of those neutrinos went right through me and you and the Earth and are still traveling through the galaxy somewhere else way beyond the Earth. But out of that 10 to the 57 of them, we detected 24. And that was enough to teach us enormous amounts about the supernova. The last time I checked, something like 1,000 scientific papers had been written about those 24 neutrinos. Okay, that's how important it was to the astronomy community. So as I said, this kind of counting, this precision counting, 24 out of 10 to the 57, is the beginning of precision astronomy. And it's only made possible by our ability to build a detector like Kamiokanda, to fill it with ultra pure water, and to build cameras sensitive enough to detect the faint light given off when a neutrino goes through the water. Okay, and this trend towards precision astronomy, not just in neutrino science, but with many other branches of science, is something that's continuing today, and it will continue into the future. And it's behind all of those awesome discoveries that you hear about on the news and when you read Sky and Telescope. Okay, okay, so that is 30 years ago. Okay, there's plenty we could talk about, but that's the basic landscape. Okay. So are there any questions we should take right now before I move on to the middle part, Bob?
I don't see any popping up here yet, but let's see.
Well, then if there's not, we can fast forward to today, to 2021. Of course, we're in a global pandemic. That's something we decided not to talk about in this talk, but astronomy is still going on. And astronomy is going on largely because of technology. This is something I didn't put in the talk, but I think it's important to mention, right? Lots of our observing is done with space-based telescopes now. Many of our observatories we can observe at remotely. Many of you who have amateur observatories may observe remotely. That is possible because of the internet and computers and remote robotic technology. And that has really enabled us as astronomers to kind of keep doing astronomy during the global pandemic. Okay, but what's the science landscape look like? That's what I want to talk about. So you remember Hubble, right? We launched Hubble 30 years ago. So what are all the things it's done in the last 30 years? One of my favorite things that we had Hubble do is we picked a few spots on the sky. And we asked Hubble to go back to those spots over and over and over and over again and just stare at that spot. And we stacked all of those pictures together and we made a single image. Okay, so these are called the Hubble deep fields. There's a Hubble deep field, there's a Hubble ultra deep field, there's a Hubble extreme deep field, but they're basically long stacks of exposures all made in the same point in the sky. How big is the Hubble field of view for these deep fields? Well, if you take a dime and you hold it out at arm's length, then the size of Roosevelt's eye on a dime is about the size of the field of view of Hubble on the sky. Okay, and if you look at one of those deep fields, what did Hubble find? Well, what Hubble found were galaxies, lots and lots and lots and lots of galaxies. In most of these deep fields, every little smudge of color and light that you can see is another galaxy. There's a couple stars in this field. You can see it there, the little star-shaped ones, those are stars, but everything else is a galaxy. And so astronomers were very impressed by this because this is what we set out to do. We set out to count how many galaxies there are in the universe and how many different types there are and how far away they are and all those questions you might ask. But if you take this image, take the Hubble deep fields, you count how many galaxies are in the image, and then you multiply by how many times Hubble would have to look to cover the entire sky, you can get an estimate for how many galaxies there are in the entire universe, because we don't think the universe is different in that direction than it is in that direction. So every direction should be roughly the same. And if we go through that exercise, there are something like 600 billion individual galaxies in the universe. Now, curiously, this number has been growing, because each time we take a deep field image, we see a few more galaxies because we go a little bit deeper. And we're getting better, not just at seeing big galaxies like the Milky Way or like M87, but we're learning that there are lots of little tiny galaxies, dwarf galaxies, not that dissimilar from the Magellanic Clouds that orbit the Milky Way. And so one of the reasons that number is going up is because we're becoming more aware of dwarf galaxies around. But the number is going up as we probe deeper and deeper. So when I started giving this talk several years ago, that number was something like 400 billion, and the latest estimates that I read are something like 600 billion. So it's fluctuating up a little bit as we count better than we have before. Okay, but this image to me, this image I think is probably the most remarkable image that we've ever taken, just because if you and I go in the backyard and we look at this point in the sky, there's nothing that our telescope can see. You cannot take a picture like the one that I showed you right here without an instrument like Hubble. It's remarkable. Okay. Now, one of the curious things about galaxies that we've discovered, and you can see many of these galaxies here in this image, are spiral galaxies. So in particular, I don't know if you can see my mouse pointer. I can't see my mouse pointer. But this galaxy over here in the center left is a spiral galaxy, not unlike the Milky Way. And one of the things that we've discovered is that whenever you have galaxies, kind of like the Milky Way or big elliptical galaxies, there almost always is a supermassive black hole at the center of them. And one of the things that we're interested in is, well, how did those galaxies get black holes at the center of them? And in particular, what are the black holes doing? And one of the things we've discovered in the last 30 years is that the black holes seem to be the thing that power the quasars. Okay, and what led us to that conclusion is our ability to study in immense detail what black holes are doing at the centers of nearby galaxies. We can see how they absorb gas. We can see how they tear stars apart. We can see how they launch these big jets that you often see in pictures coming out of them. And we can see what kinds of light they give off and what the spectral profile looks like. And if we look at all of those different things, we can learn by studying black holes near to us. And then we go look at the quasars. We discover the quasars have many very, very similar properties. So we took Hubble and we looked at the quasars, and what we discovered is every quasar that Hubble looked at was surrounded by a galaxy that was too faint to be seen unless you use a telescope with the capabilities of Hubble. So the Hubble Space Telescope enabled us to discover that the power behind the quasars was supermassive black holes, and that they are indeed just very early, very distant galaxies. Okay, so that mystery is resolved. There are other mysteries we still don't know, like how did black holes get that big that early in the universe? That's the current big mystery about quasars. But we know today they're supermassive black holes, and we know that they live at the hearts of early type galaxies. Okay. Now, this is kind of an interesting point, because black holes, I would say in my lifetime, in my career, have gone from being something that those of us who think about relativity and gravity and theory have been able to describe for a century or more. But in just the last 30 years, they have become a central mainstay in astronomical thinking. They are needed to explain many astrophysical phenomena, and many observational tests have been conducted to probe whether or not the objects causing these things to happen, stars are disrupted, stellar clusters at the middle of galaxies, the quasars themselves, can be caused by any other phenomena. But in every case, every one of those observational tests has matched perfectly with the predictions for what black holes have done. So astronomers have come to embrace black holes as a natural part of the astronomy landscape. Okay, and that's a big change from when I started in this field. The most distant object that we can see is the cosmic microwave background. This is a diffuse glow of microwave light that you can see on the sky. It was emitted when the first atoms formed, which happened something like 400,000 years after the Big Bang. This is as far away as we will ever be able to see with telescopes that observe in light. There are ways to probe past this with neutrinos or with gravity, but with light, with conventional telescopes like you and I are used to thinking about, this is as far back, the most distant place in the universe that we will ever be able to see. When I had just started in graduate school, this picture was a flat pink blob. We just knew the microwave background was there. That was a tremendous measurement to start with. But over the ensuing 3 decades, what we've seen is this little individual structures showing up. And what these spots are basically hot spots in the cosmic microwave background, the sites where galaxies would eventually form and become the galaxies that we see today. So this is the beginning of what we call precision cosmology, the ability to make measurements very precisely on very tiny scales at enormous distances in the universe. The largest telescope, the largest effective telescope today are the twin 10-meter telescopes on Mauna Kea in Hawaii, the so-called Keck Telescopes. These are the telescopes that supplanted the Hale telescope. So they became the largest when Keck 1 came online, acting by itself. When Keck 2 came online, the technology was devised to combine the two signals. And so today, these are effectively the largest telescope on the planet. In all, there are some 18 telescopes around the world today that are larger than the 5-meter telescope in Hale. So the Hale telescope is still one of the biggies. It's number 19, I think. But there are 18 more that are in this class of 8, 9, 10 meters. Okay. Telescopes are also getting bigger for amateurs. So this is my current Dobsonian. So the Dobsonians I showed you earlier are 8 or 10 inches. That was kind of very common 30 years ago. Mine is by no means the largest telescope you'll see at a star party. This one's only 22 inches. You'll see 36 inches. I've seen the 48-inch telescope that amateurs have at star parties. So the Dobsonian technology has enabled even those us amateurs to observe in our backyards to have bigger telescopes as well. And of course, bigger telescopes you can see more. We want them for the same reasons that professional astronomers want bigger telescopes. We talked about the supernova, 1987A, and supernovas create the naturally occurring chemical elements. There are 92 known naturally occurring elements. They're the things you learned about when you studied the periodic table in chemistry class. But one of the things that has happened in the last 30 years is our ability to take a census of what the cosmos is made of has increased dramatically. And what we've discovered is that these 92 naturally occurring elements, atoms, only correspond to something like 4% of everything that we know exists in the universe. What's the other 96%? Well, 23% is something called dark matter. We've been aware of dark matter for a long, long time, since the 1930s. It influences gravitational dynamics on the scales of galaxies. We can observe its influence on how galaxies rotate. We can observe its influence on how stars are distributed. There's lots of lines of evidence that point to the dark matter being there. But since the first paper written about the notion that dark matter was there and that we could see its effects observationally, we have yet to discover what it is. And when I was in graduate school, this was the big mystery. What is dark matter? And I would say today, it is still a big mystery. What is the dark matter? Just 20 years ago, we discovered the so-called acceleration of the universe. And those of you who have done a lot of reading about cosmology may be familiar with this story. We were looking at supernovas and their light profiles were not as we expected. And the explanation for that is that the expansion of the universe is being influenced in unusual ways by some unseen something that we call dark energy. And we can measure precisely how much there is, and that dark energy consists of something like 73% of the entire quantity of stuff that makes up the entire universe. Okay, so these two things together, dark energy and dark matter, are really central mysteries in astrophysics today. They have been for the last few decades, and I expect they will be for several decades more. We're getting better at measuring their effects, but we have yet to have any good luck at determining what they are. Okay, and so this is something that my colleagues and I, we spend lots of time thinking about, and some of us work on it, and we think of new and clever ways to measure them and to constrain them, but we still don't know what they are. And I can give you a whole talk about this sometime if y'all want to hear that at Sun River. Okay. I will say that unfortunately, Pluto is apparently no longer a planet. There are some of us who agree with that and many of us who don't, but Pluto has been demoted. That happened to much fanfare about 15 years ago now. So I give an entire talk about Pluto too. I will say that that demotion is nothing to do with Pluto. Right? Pluto is no different now than the day it was discovered and the day we classified it as a planet. What it has to do with is our very deep uncertainty about what we mean when we say the word planet. Okay, and the reason we have deep uncertainty has a lot to do with our ability to look at the solar system and our desire to classify everything. Okay, but what's really driving our uncertainty about planets is the discovery of planets around other stars. If you had asked an astronomer the day I walked into graduate school what they expected solar systems to look like around other stars, they would have told you they expected them to look a lot like our own solar system. But now, today, we have discovered 4,902 planets as of this morning around other stars. Some 800 of them are in multi-planet systems, and none of the multi-planet systems that we know of look like our solar system. And this is causing a lot of consternation right now. We don't know, is our solar system the norm or is it unusual? And the way you answer questions like that is you go out and you find more examples. And so in the last 20 years or so, we have been refining our ability and our techniques and our observing plans for discovering planets around other star systems. And right at the beginning, when this was first happening, they were coming fast and furious. We would get announcements every couple of weeks that we had discovered new exoplanet systems, as we call them. But today, the catalog is enormous. Missions like Kepler and currently TESS, the transiting exoplanet system surveyor, I think is what TESS stands for. They are observing stars over and over again. And as this image here shows, they are watching for small planets to transit in front of their parent star and cause the light from the star to go down just a little bit. And from that measurement, you can measure the size of the planet, you can measure the speed of the planet's orbit, and start gathering its characteristics. Okay, so this pile of data is changing our ideas about planets every single day. And in many ways, that's good because it teaches us where our thinking is very limited and needs to be broader. But in other ways, it's very bad because there's so much data, there's so many different things to explore that we can't possibly explain everything that the data might be able to tell us. And so consequently, there's an enormous effort underway right now, both to process and recognize data, but also to simulate solar systems on the computer in an attempt to explain the planets that we see in the data that we can take now. So this is really a tremendously hot field in astrophysics right now. There's lots of people doing observations. There's lots of people imagining new missions. There's lots of people doing chemistry. There's lots of people doing geology. There's lots of people doing orbital dynamics. All kinds of people in all branches of science are working on this problem because for the first time, we know that there's planets around other stars. And not just we know there's planets around other stars, we can measure their properties. And measuring their properties is the beginning of being able to have some semblance of knowledge about what these things are all about. Okay, so this is going to continue to change. And when I come back and talk to you 30 years from now about what the future really held, this is going to be a huge part of the story. Precision astronomy has also been continuing. So many of you know I'm a gravitational wave astronomer. That's what I actually do for my professional astronomy. So I study the universe not with telescopes, but with gravity most days. And 6 years ago now, we made the very first discovery of gravitational waves from the universe. There have been many, many discoveries since then, and the discoveries have been remarkable. They've been changing our understanding of the nature of stellar evolution, the nature of stellar mass black holes, and how gravity itself works. So there are many gravitational observatories around the world. There's, I think, 5, there will be 5 soon. There's currently 4 active ones. The 2 most famous ones are here in the United States. They're called LIGO. One's called LIGO Hanford, not far from all of you there. It's up by Tri-Cities. And the other is down near Livingston, Louisiana. So it's called LIGO Livingston. If you go to the LIGO Hanford site, they are building a visitor center there. And I don't know when it's supposed to be done, hopefully in the next year or so, I don't remember. But there will be an opportunity to stop in and you can certainly learn all about LIGO and the sorts of science that they do there. These are not telescopes in the ordinary sense of the word. They look like gigantic L's on the in the Hanford case in the desert there. The distance from the corner building that you can see right there all the way to the end of that arm that stretches diagonally across the screen there is 4 kilometers. They're basically enormous tubes. You can see in the upper right there, the technician standing inside one of the tubes. Our telescopes are actually laser optics, and we shine lasers up and down those arms, and we monitor how long the laser takes to fly up and down the 2 arms of LIGO. The reason we do that is gravity, which we use, gravitational waves, what they do when they pass through LIGO is they stretch the arms of LIGO by tiny amounts. And we can detect that with the lasers and from the stretching determine what it was that generated the gravitational waves, neutron stars, black holes, whatever they might be. Okay. Now, the interesting thing about that is I said this is precision astronomy. If you were to scale the stretching of LIGO up, you were to take LIGO's arms and stretch it from the Earth all the way to Alpha Centauri, and then you have a gravitational wave go by, the arm would have changed size by only 10 micrometers, by the width of a human hair. Okay, so that's the precision to which we are able to make that measurement. If you shrink LIGO back down to its normal size, the measurement that we actually made here on the surface of the Earth is we could detect the stretching of the LIGO arms by a factor of 1/1000th the diameter of a proton. Okay, so this is extreme precision astronomy. but it is commonplace. We can do it. We've done it many times, and we continue to build new detectors capable of doing it to expand our ability to observe the universe. Okay, what are we detecting? Well, we're detecting things like this. This is a movie showing two 30-ish solar mass, a 29 and a 36 solar mass black holes going around each other. Okay, this whole movie is slowed down. The event that you're watching happen right here in the movie takes only a couple of seconds to actually occur. The black holes get closer and closer together, and eventually they merge to form a single new black hole. Okay, and that all happened 1.3 billion light years away. And as they move around each other, they stretch and distort the gravitational field, and that information propagates across the cosmos until it washed across our detectors at LIGO. Okay. Now, this is a movie, right? The sort of stuff Hollywood does, right? This is generated on a computer. No one saw what you're seeing in this movie. And that's because our data in gravitational waves is not visual data. We don't actually have pictures the way Hubble has pictures. And so we have great difficulty as gravitational wave astronomers helping people understand what our data is really like. And so one of the things that we've settled on is showing people that the data can be interpretive and thought of more like sound than it can be a picture. Okay, and so this is a picture of what our data actually looks like. So these little squiggles here on the bottom and the colored background in each of these images. If you're a gravitational wave astronomer, you're used to looking at these all the time. We're like, whoa, look at that black hole, because I've seen enough of these, I can recognize they're black holes. But for a person who's not a gravitational wave astronomer, it just looks like a bunch of wiggles. It looks like the sort of thing you see at the doctor's office when they put an EKG on your heart or something, okay? But they are in fact signals from black holes far across the cosmos. And so what we can do is I can take these wiggles and I can push them out through the headphone port on your iPhone, and it will turn this signal into a sound that you can listen to. It's not really a sound. It's just a way of representing the signal so that your brain can process it. Okay, so I've done that here, and I'd like you to listen to this signal, which was the very first gravitational wave signal ever detected. Okay, so the first time it goes through, it'll be real time. And the second time it goes through, it's sped up by a factor of 2. And that speeding up is just to make it a little bit easier for your ear to hear, but it's the same data either way, it's just sped up. So let me play that for you. Okay, so that signal is very faint. It kind of sounds like a heartbeat. And then the second time when we speed it up, it goes whoop. We call that the chirp. And that's that very last state where the two black holes come together and merge. And from that signal, we can determine how far away they are. We can determine how massive they are. And for some cases since then, this first one, it was very hard. But for some cases since then, we can tell you if they're spinning, because it changes how that sounds. Okay, so it's a remarkable technology. We're very brand new at this, the same way Galileo was brand new with his telescope, but we're learning how to do it better. And at this point, we're getting better at it than we expected to very rapidly, because there's a lot of this stuff going on out in the universe. Okay, now I would be remiss if I went through today if I failed to mention that at the end of next week, on December 24th, we will be launching the successor to Hubble. When I started graduate school, this was just an imagined telescope. It was called the Next Generation Space Telescope. But those of you who are following along know this is called the James Webb Space Telescope. It is the largest telescope ever put in space. It is 6 meters across. And right now it is all folded up inside a rocket. It will launch next Friday. It will take about a month to get to where it's supposed to be. And then origami style, it will unfold into the telescope that you see here today. The James Webb Space Telescope is going to be looking for the first stars in the universe. It's going to be looking at all those early galaxies, the kinds that we find quasars around. It will be studying exoplanet formation. There's all kinds of science that this telescope is going to be capable of. And it is the telescope that 30 years from now, we will be talking about the way you and I are talking about Hubble tonight. So watch for that. That should be a week from Friday. Okay, so Christmas Eve launch for the James Webb Space Telescope. Okay, you can drink some eggnog and watch the launch on NASA TV. So, okay, so let's jump to the future and then we'll tie the evening off. So let's jump 30 years into the future to 2051. Okay, so what will astronomy be like in 2051? The discovery of exoplanets is not slowing down. We will know many, many, many more solar systems than the ones that we know today. The difference that most of us expect for 30 years from now is that we will have detected and characterized planets around other stars that are, as we say in the business, Earth-like. And what we mean by that is we'll have measured their size, their mass, and we should have been able to measure their atmospheres. We're developing the techniques right now. We're proposing new missions, but we're learning how to use the telescopes we have to measure the atmospheres around these planets. And we're looking for things like water. We're looking for the kinds of biochemical signatures that we see in Earth's own atmosphere to see whether or not we can detect Earth-like planets around other stars. So 30 years from now, that will have happened. As we've mentioned several times, computing and simulations are going to be more capable. Computers are getting bigger and faster, but they're going to be more important than they are today. So the kinds of things we simulate today are colliding black holes. My group here at Northwestern, we simulate entire galaxies, stars through their entire lives to see what they become through the entire galaxies. And then many of our colleagues, as you can see up there in the upper left, are simulating the explosions, the supernovas of individual stars. And so this is one of the reasons we would love to see a supernova in the Milky Way is we need a lot more information to help inform us how to do those supernova simulations much better. So this is core to astronomy today. Our instruments are getting so good at collecting data, and we have so much data that we can't understand it without being able to do these kinds of precision simulations. Okay, it's needed to interpret the data. Telescopes, even on the ground, are getting larger. I showed you JWST. It's going to be about 6 meters across, but we are rapidly approaching telescopes that aren't 10 meters across, but are 30 meters across. There are several such telescope efforts underway. This is a famous one called the Giant Magellan Telescope. It's actually a multi-mirror telescope, and this and many others like it are going to be online in the next 10 years or so. Observations will begin very soon. Okay. Astronomers, of course, are imagining enormous telescopes. So this is one that I think we've decided isn't going to be built, but I like to show it to people just to show that astronomers really do think that the impossible is possible. I will point your attention to the little white flecks in the bottom of this image near the dome. Those are trucks. So this is a proposed 100-meter diameter telescope. The telescope is so large that the easiest thing to do is to just move the entire dome off the telescope when you want to observe. Okay, so that's what you see there. The dome itself is on tracks. It just rolls off the telescope. This telescope was called OWL, O-W-L, the Overwhelmingly Large Telescope. Now, as you might imagine, such telescopes are expensive. They will cost billions and billions and billions of dollars to build. And one of the things that we are struggling with as astronomers is, do we really need telescopes this big, or can we do science with smaller telescopes and still get really great results? And arguably the answer is yes, which is probably why we're not at the moment planning to build a 100-meter telescope. But our engineering friends think it's possible. And so it may be, those of you who are 10, 11, 12 in the audience, by the time you're 90, maybe we'll be building telescopes like this. So I'll bet anyone a bag of jelly donuts and a Dr. Pepper that 30 years from now, we probably still won't know what dark matter and dark energy are. I shouldn't say that because I work on some experiments to try and measure what the dark matter is. But I am pessimistic just because we don't really seem to even have a clue at the moment. And it's been that way my whole astronomical career. And so I'm I'm willing to risk a bag of jelly donuts and the Dr. Pepper that we won't know what dark matter and dark energy are. Okay, but we're going to be awesome at observing it, right? And we're getting better every day at observing it, but we still don't have any. I don't think we have any good thoughts about what it is. Our study of the universe in gravity is going to continue. This is actually the primary observatory that I work on. It's called LISA, the Laser Interferometer Space Antenna. Rather than building big concrete tubes in the desert like we did for LIGO, we'll have 3 spacecraft in outer space that shine lasers back and forth between each other. And with that, we will be able to detect gravitational waves from the distant cosmos. So LISA is due to be launched in about 10 or 11 years. And so 30 years from now, it will be well through its observing mission, and we'll have some awesome stories to tell you about the sorts of things that we've discovered with gravitational waves and precision measurements from space. Okay, so I am right near the end of the hour, so I'm going to jump here to the end. So we really are living on the frontiers, and in many ways, if you go back and you look at the history of astronomy at any given moment, we're always living on the frontiers. We're always observing at the limits of what our capability and our technology lets us observe at. And we're always trying to answer questions that have really mystified us and we don't have any clue. That's just the nature of how astronomy is. And so anyone who ever says to you they think astronomy is over or we've discovered all the things, I really think that is patently false, as the entire history of astronomy has continued to prove. So I think as an astronomer, as a professional astronomer, and as an amateur astronomer, this is certainly a very exciting time to be living in, just because we're discovering really remarkable things. And of course, the thing that's always the best is, there's stuff we haven't even imagined yet that we're going to discover with our telescopes, whether they be traditional telescopes, gravitational telescopes, astroparticle neutrino telescopes. We're going to discover things that we don't know what's going on. And that, of course, is what the grand mystery and the grand appeal of science really is. Okay. So I always like to leave you with a few things to read. These are a few books that I think are quite useful. Those of you who are amateur astronomers are probably familiar with the one there in the lower right. This is called 365 Starry Nights by Chet Ramo. It's one of my favorite books for people who are just getting introduced to the universe. It has an entry, as it suggests, for every night of the year that will let you walk out in your backyard and show you something you can see, typically with your naked eye, and connect it to something that modern astronomers think about, whether it's the evolution of stars, the nature of the galaxy, the history of how we discovered something. It's really a quite beautiful book. The universe book there in the lower center is a very nice coffee table book. Those of you who are familiar with DK books know that they're just replete with glorious images, but I like this one because it's encyclopedic. It kind of has 2 pages about everything. So if you're interested in meteors, there's 2 pages in meteors. If you're interested in quasars, there's probably 4 pages on quasars. So it's very readable if you want to do very specific things. Einstein's Unfinished Symphony is a book about LIGO and the first discovery of gravitational waves, if you get the 2nd edition. So if you're interested in the growth of precision astronomy, that is one place to start your studies. And then right there in the upper center is a book by Marcia Bartusiak. Both Einstein's Unfinished Symphony and The Day We Found the Universe are by Marcia. Marcia is a very good science writer, and The Day We Found the Universe is about the discovery of the expansion of the universe with the biggest telescope of the day by Hubble in the 1920s. So that's a very nice book for those of you who are interested in how our understanding of astronomy changes dramatically based on single observations. And that's a great example of how that happened. And then lastly, we've talked about the universe on very large scales, from the solar system all the way to the outer solar system. And so I always like to remind people of this very famous movie that was made in the 1970s by the Ames brothers at IBM. You can find it on YouTube. It's called Powers of 10. It zooms out from a picnic here in Chicago, actually, in our waterfront park, all the way out to the distance of the quasars, and then it zooms back into the scale of the quarks and the neutrinos. So it's a very nice movie for that sort of thing. So, okay, so I am going to end my chitter chattering at you there and say thank you very much for your attention. And if there are questions, I'm certainly happy to answer some for a few minutes.
So Shane, we do have a couple questions both in chat and
okay,
during the Q&A. We can probably start over here with the Q&A. One of the first, Robert wanted to know, how were neutrinos first discovered?
So the neutrinos were proposed before they were discovered. In the 1930s, I guess it was, when they were first starting to try and understand nuclear physics, they were measuring the energy in nuclear physics reactions. And what they discovered is that the amount of energy they thought to come out, they couldn't measure it all and find it. It was vanished. It wasn't there. And so I think it was Pauli, Wolfgang Pauli, proposed, maybe it was Fermi, I forget which one it was, one of those two guys, proposed that there was a particle that had not been detected yet that was carrying the energy away by virtue of its enormous speed. And so they called this particle the neutrino, the little neutral particle. And they went, I think it was Thompson or Chadwick, I'm forgetting all my physics history, who did a laboratory experiment to actually measure the first neutrino detection. And the way you detect neutrinos is you detect them by interacting with other particles. So for instance, the neutrinos are generated by taking an electron and a proton and smashing them together, and it makes a neutron. Well, when the neutron decays, it also produces, in this case, an antineutrino. And so you can devise experiments where you can detect them. So that's the way it was first detected. But these ones that I just told you about by supernova 1987 were the first, I think they were the first ones from extragalactic neutrinos detected.
Okay. And then this is a great question. Rich asked a question about the raft.
Uh-huh.
You know, the idea of making the water dirty or polluting the water, which I thought was a great question. Yeah.
Yeah, so I don't work at Super K, but I've had this exact question myself, right? So they obviously have to purify the water somehow. And if you go back and you look at that picture, can I get to it quickly? You'll notice they're all in what we call bunny suits. They're the clean room suits that we measure so that that we wear so our skin and our hair doesn't contaminate the environment that we're in. And if you look at the scientists in that picture, you'll see they have their clean room suits on. That's the white suits that they're actually wearing. So they're doing their best to keep it from being contaminated. And I don't know what kinds of things they go through on the raft to actually do it. There's a similar observatory to this in Canada. It's called SNO, the Sudbury Neutrino Observatory. And that one's even worse than this one because the water in SNO is not ordinary water. It's heavy water. It's water that's been processed through a nuclear reactor. And so it has to be purified in completely different ways because it's a precious resource. They basically convinced the government of Canada to give them Canada's entire supply of heavy water to build Sudbury. But I don't know how they clean the waters. That's probably a good thing to troll around their website and see what they say. That's a great question.
Robert had a good question. I know there's a few staff here on the lecture tonight, and we get this question all the time. So the question came up: what is a black hole? So your definition, when someone asks you, what is a black hole?
Right. So the definition of black hole that I use is the classical definition of black hole. Okay. And of course, there's a more sophisticated relativity discussion to be had. But the definition, the observational definition, is a black hole is an object whose gravity is so intense that at the surface of the object, light cannot escape. Okay. And what that means is nothing can escape because Einstein taught us that nothing can travel faster than the speed of light. Okay. Now, a more detailed relativity discussion about what's the inside of a black hole like and all of that sort of stuff, that's way more complicated, but that's not observationally accessible. So from an astronomer's point of view, all we have to talk about is the observational definition, which is from the outside, it's an object from which not even light can escape.
Okay, great. And then Debbie had a question about the cost of your, like you showed a picture of your Dobsonian.
Yeah.
22 inch, I think. And I just briefly sent her a note saying, well, our 20-inch Star Masters run about $14,000. But they were produced telescope way back in the day with a drive and all that kind of stuff. But yeah.
Yeah, so that cost, if you buy a commercial 20-ish telescope off the market, I think that's still roughly the right cost, kind of $10,000 to $12,000. I built mine, so all the infrastructure I did myself, so I save a lot on cost that way, and I just paid for the mirror. So the mirrors are still pretty expensive. I think my mirror was $5,000 at the time I bought it. I had Carl Zambuto up in Washington make it for me. So,
Oh, okay. Yeah. Let's see. Question about the James Webb. How soon will we get images back? And I was under the impression it was pretty soon in 2022.
Yeah.
I know it's been delayed launch and all that, but
all that stuff, right? Yeah. So it will take a month to get to where it's going. They will have to unfold it and do the system check, and I don't actually know how long that takes. But they will take what's called a first light image. And actually, NASA must have said, but I don't think I've seen, there's always some object they've picked for the first light image. And so we will see the first light image when they take it, but I would expect it should be in the first quarter of 2022. So sometime before March or April, but and that's just given the time scale for cruising, unfolding, doing the engineering check, and astronomers are just in line right now waiting for it to happen. So they're gonna want to get up to science operations as soon as they can. It may also need to cool for a little while. Maybe that's the other thing that has to happen. So underneath it, it looked like it had those big panels of aluminum foil. Those are basically a sun shield. They sit between the telescope and the sun, and the telescope has to cool down to the ambient temperature of space because it observes primarily over in infrared. And actually, I don't think I've seen how long that cooling process takes, but I don't think they're going to wait for it to be fully cooled before they start taking images. So yeah,
I'm sure it's like getting a new telescope. You want
exactly, yeah. So
yeah, Steve had a question about the age of the universe. I think you used 14.6. He was thinking more of 13.8.
Yeah, so that's a good question. So that number fluctuates back and forth. And the reason it fluctuates back and forth is because the way we calculate that number, we take many different astronomical measurements together, and then we fit them all together and try and find the most consistent answer. And so to be honest, that's a number I didn't double check before I gave the talk this time. So it's entirely possible that since the last time I gave the talk and this time that the number's gone down. The primary influence on that age, on that number, tends to come from the cosmic microwave background and the dark energy measurements. Those are the two big drivers at the moment. But just in the last couple of years, we have started to be confused about what the actual value of the Hubble constant is again. So as astronomers say, there's tension in our measurements. And what that means is some measurements are predicting a value higher, and some measurements are predicting a value that's lower, and the measurements don't seem to overlap. And so we're trying to understand that right now. And the Hubble constant does go into the calculation of the age of the universe. And so that may also be a source of the discrepancy between the two numbers at the moment. So it's entirely possible that the current best number astronomers use is not the number I quoted you, but you're absolutely right. It fluctuates right there around 14, from the high 13s into the low 14s all the time.
So Debbie wanted you to put your first slide up for your contact information. If you can.
Oh yeah, I can do that, no problem.
And then while you're doing that, Lee had a question about, this is a great question, actually. I never even thought about this, but what software, language, tools, and computers do you use for your simulations?
Yeah, so the software of choice for many astronomers today is Python. Largely that's because there is an enormous open source astronomy software community that has produced lots of tools that we all share and use, which allows us to be confident that we're doing calculations in the same way. For those of us who do really high performance computing and we need a little bit more speed out, it's probably generational. I use C, or some of my colleagues use C++, but folks who are older than me still use Fortran.
I remember that.
So all of us have to know a little bit of Fortran because every now and then we get some Fortran codes. But I would say Python and then C are probably the most common programming languages. Tools like Mathematica, MATLAB, these sorts of things are also very common, but for not for gigantic simulations of the sorts I've been showing you. For the simulations I showed you tonight, we're using full-blown languages. So.
Okay. And I love this question. Scott was asking, what are your thoughts on multiverse?
Yes.
Yeah, which is
Yeah.
something. I mean, we just finished up my my finals for class, and that was like the whole multiverse thing. So
yeah. So multiverse stuff. So I'm actually a physicist by training, and so multiverse stuff is interesting because there's many branches of physics which latches onto this notion about multiverse, and that starts from string theory and field theory and quantum mechanics, and then in cosmology it goes into the fact that into this question of how is the universe connected to other places in the universe? And are there places in the universe that are disconnected to us just by virtue of the size of the universe, right? And so one of the things in cosmology that very early on I studied in graduate school was something called a domain wall. Okay, and so a domain wall is a gravitational barrier in the universe where on one side of the universe, it's a universe like ours, where the speed of light has its value and the gravitational constant has a value. But on the other side of the domain wall, the physical constants are completely different. And so that universe is not a universe that you and I can live in or exist in or survive in because atoms as you and I know them wouldn't exist over there, right? So there's that kind of multiverse stuff that people talk about as well. So I guess maybe my question is, what type of multiverse are you asking about? And then there's, universes through black holes and universes through wormholes. Those are also different stories too.
let's see here. There's a lot of good questions coming in here. I got to go back to this one before I lose it here. We had Lucy had a question about antimatter.
Okay.
So let's see here. There it is. Do you know anything about antimatter? From Lucy, age 10.
Okay.
Perfect.
Yeah. So Lucy, antimatter is, you remember I was telling you the story about neutrinos. And right about the time that physicists were first thinking about neutrinos, they were also thinking about antimatter. And antimatter is definitely a thing. We can make it in the laboratory. So when you go to college, many colleges in their physics labs, they'll have experiments where you'll make antiparticles, as we call them. Antimatter is just like ordinary matter. It's like the stuff that you and I are made of, but some of its properties are different. Okay, so if you've learned about atoms in your body, in your pencils, in your paper, your computer, everything, are made of three kinds of particles: a proton, a neutron, and an electron. So let's just talk about the proton as an example of antimatter. A proton is what you and I call matter, and it has certain properties. It's a certain size, but most importantly, it has an electrical charge that we call plus. Okay, it's a positive charge, as we say in physics. And the difference between a proton and an antiproton, the antimatter version of the proton, is that they look exactly the same in size. The only difference is an antiproton is negative. Okay, and so that's very interesting. And we can make antiprotons in the lab. And the interesting thing is if you take an antiproton and you put it next to a proton, they destroy each other and just become a particle of light. Okay, so that's why it's very hard to have antimatter around, because everything that you and I have, our beakers, our flasks, our containment devices, are made of ordinary matter. So if you're going to contain antimatter, you have to have ways of containing it without touching it, which is why it's hard. The interesting question for astronomers today, and we do not know the answer to this question, is why is so much of the universe made of matter and not very much of it's made of antimatter? Because the way the universe normally works, everything likes to be in perfect balance. but that is certainly not the case. The universe around you and I seems to be made of matter, and we don't know the answer to why that is. And that's something that many people in astronomy and many people who study this kind of quantum nuclear particle physics stuff that we've been talking about, this is a question that occupies much of their time trying to understand what the answer to that question might be.
Yeah, that's a tough one.
It's a tough one. Yeah.
It is a tough one.
So when you go to college, you should figure out the answer and then let me know.
Yeah, so that brings up, Bonnie had this great question, when you had your pie chart up about antimatter, and so
about dark energy and dark matter.
You're trying to understand the 70% part, that we don't know what the stuff is, but we can see it, which I think is a great, like you said, even 30 years from now, we probably won't know what it is,
right?
But we can see it.
We can see its influence, right? Yeah. So this is, I mean, the dark energy in particular is an interesting one, because we've known about it for only about 20 years. And the first 5 or 6 years after the first measurement, I mean, physicists weren't even convinced that the measurement was correct. Right. And still today, right, we've had such a difficult time of trying to understand what this stuff might be that, I mean, just a couple of months ago, I heard another talk about maybe we're not measuring the supernovas correctly, right? And so we're still trying to wrap our brains around what this might be, because it's clear something's going on, and it's not clear what it is. And so we're still uncertain enough that we doubt ourselves. And as scientists, whenever we doubt ourselves, we go back and we check our data again. We make new measurements. And constantly we keep coming back to, yeah, it looks like we did it right. This stuff must be there. But what is it? That we just don't know. So.
Okay. And then there was another great question here. There's some more questions popping in, which is awesome. Okay, so this is a great one. You went 30 years ahead. So this question came from Daniel. Want to know, do you think we'll discover life elsewhere in the universe in the next 30 years? And before you answer, one of my running things that I talk about in my class, I actually believe the kids that are coming, like Lucy and the folks that are coming to the observatory, I believe they'll find some form of life form in our solar system.
Yeah.
That's my opinion, but I'll let you take the universe question. Yeah.
No, well, so I actually agree with that. We'll probably find it in the solar system first, right? The difficulty in the solar system, of course, is when we do find it in the solar system, the question is, where did it come from? Was it really there, or did we put it there, by throwing space capsules at the moons of the solar system or something? But the question about finding life outside the solar system, though, is really hard, because the difficulty of detecting life in the solar system, assuming it's not contamination from us, right, throwing tardigrades at the moon or whatever, is we're not even certain that we recognize life when we see it on Earth, right? One of the great transformations in astrobiology here in the last 2 decades or so has been the recognition that here on Earth, life exists in very unusual environments. It exists in places that a decade ago we didn't think life could exist. And the way life processes, the way it generates energy, the way it propagates, it can do it in ways that are unusual compared to any way that we thought about life in the past. And so this idea that we will recognize life when we see it is one that I think in astrobiology we struggle with a lot. And that problem is amplified 1,000 times more, if not more, when you go outside the solar system. Because outside the solar system, looking at planets around other stars, you're never, ever, ever, ever going to be able to do an experiment. All you can do is sit here and look. We're going to have some chemical signature of an atmosphere. We're going to see some, different signature of water, or who knows what, right? But none of that is incontrovertible evidence for the existence of life. Right. So those of you who follow this, you remember the phosphine discovery in Venus's atmosphere about a year or so ago, right? That phosphine is a very unusual molecule which can be connected to life processes, and it was unexpectedly detected in Venus. Does that mean there's life on Venus? Well, Who knows, right? We'd never seen phosphine there before. We'd never thought about there being phosphine there before. That's what it's going to be like around other planets. But you know, we can't even answer that question here on our own solar system, even though we could go to Venus and look for life, right? It's going to be that much harder to answer the question around another star. Now, the only way that it will be actually incontrovertible is if we get a SETI signal, right? If they are beaming data at us, you know, the prime numbers, and they're coming clearly from a star 25 light years away, then we'll be like, yeah, that's not us, right? So that's probably the only way we'll be certain. But then, of course, everyone will be like, is it a hoax? Is it one of the Starlink satellites, right? We're going to have to go through all of that process as well. So we'll see.
Okay.
But the important part of that question is we're looking, we're trying to find life around other stars. We're trying to detect biosignatures in atmospheres. We're trying to think about ways. We're doing optical SETI searches, looking for lights from cities and nuclear explosions or whatever, right? So we are looking, but the question is if I walked in your office and handed you some data, how would we decide with certainty that we had detected life or not? That's the hard thing. So.
Yeah, I'm glad I don't have to make that call. We had a question about Pluto. Can it be called the ninth planet again?
So there are those of us who argue that it should be. Okay. Now, if you go listen to Alan Stern, the guy who led the New Horizons project, he thinks much like I do. But if you go listen to Mike Brown, whose book How I Killed Pluto and Why It Had It Coming is a great read, Mike has a slightly different take on the matter. And Mike's point is that Pluto doesn't look like all the other things that we call planets. It's icy, it's small, it's far away, blah, 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 blah. Long list of reasons. And they're all great reasons, okay? But by any sensible definition of planet that we would apply to our own solar system or other solar system, and we can argue about the definitions astronomers are using right now, Pluto really should, to many of our minds, be counted as a planet. The idea that it's different than the other planets and shouldn't be called a planet is, I think, in some way crazy, because the Earth and Jupiter don't look the same, but you call both of them planets, right? So why are you separating out Pluto's properties and calling it not a planet, right? So there's arguments to be had there. But as I said, they're healthy arguments, right? Because they're arguments that astronomers are having because we're trying to quantify what we mean and what we know about objects that we're going to call planets. And 100 years from now, we may decide that it should be a planet. But, you know, that will depend on what we discover on other worlds. That will depend on what we discover in the Kuiper Belt. All kinds of things will influence that discussion. In the end, we can measure its properties and we know what it is. And the planet is just a label. It doesn't change the fact that Pluto's there and it's going around the sun and it has properties to study, right? But whether or not we call it a planet or not is influential on how we study how solar systems form, for instance, right? That's the reason the nomenclature is important, is because we use the nomenclature to communicate with each other.
That's great. Yeah. So we got a couple more here, and then we'll turn it over to some staff questions here. Joseph wanted to know, can artificial intelligence techniques be used to look at data for interesting astronomy events like new planets or something like that?
Yeah, absolutely. So one of the kind of growth industries in astronomy right now is developing techniques that use machine learning in particular to do astronomical tasks. And in many ways, that's essential because there are a lot of astronomical missions and observatories coming online that are generating more data than humans can physically look at. Okay, so the famous ones right now are ones like the Zwicky Transient Facility and the Palomar Transient Factory in Southern California, Catalina Real-Time Survey, a couple of others, but most famously the Vera Rubin Observatory, which will start observing here very soon, what was used to be called LSST, right? Vera Rubin is going to generate something like 10 million transient signals a night. right? And so we cannot, as humans, physically look at all of those. So we are training machines to look at all the light curves and separate them into, these are the things that look like asteroids. These are the things that aren't anything. These are the things that look like cataclysmic variables. These are possible supernovas. And then it divvies up the data and sends it out to everyone who's interested in rotating asteroids or whatever. So we absolutely need machine learning just to process the volumes of data that we're capable of collecting today. In my field, in gravitational waves, we are learning how to use machines to search for the signals in our data. And that's because many of the signals we're searching for are very faint. And machine learning algorithms are very good at seeing signals sometimes that a human eyeball is not. And it can detect the signal and generate the statistics for the confidence and how well we've detected it and everything far better than me or my students could do. So we're learning to use that in our analysis techniques as well.
That's great. Okay, we'll do one more here and then we'll kind of go off to a different direction here. But Steve was asking, he was trying to comprehend the shape of the universe, and he's kind of stuck on that three-dimensional concept with maybe the influence of, of time. Well, it's hard to visualize infinity from a size standpoint. It's harder time understanding the finite universe. So if so, what lies beyond? I know you touched on that a little bit on the multiverse.
Yeah. So this is the age-old conundrum in astronomy, right? Is how do you wrap your brain around this? And I will preface, or maybe I'll just say, the hardest part about this is that we are very sloppy in our language. Okay, even I'm very sloppy in my language, right? We will talk about the universe, and we've never sat down and agreed upon, you and I in our conversation, what we mean when we say the universe, as I've printed here on this slide, okay? What the universe, capital T, capital U, means is everything that exists, okay? But when we're astronomers and we're talking about observing, we will often say the universe, and what we mean is the observable universe, which is not everything that exists. It's the things that exist that have had time to send us a signal, right? So the observable universe is a finite little section of the universe that light has had time to travel to us from in the 13.9 or 14.4 billion year age of the universe. Okay, so when I explain this to people, it's often easier to think in terms of the everyday experiences, which is if you've got a car that can go 90 miles an hour and you have exactly 1 day to drive, the accessible part of the countryside is not the entire country, right? It is however far you can get in 1 day driving at 90 miles an hour. And that's what the observable universe is. It's how far light can get in the age of the universe. Okay, and that's different than the universe, which is everything that exists. Now, astronomers ask, right, the observable universe is finite because the speed of light is finite. So things can only travel a certain distance, okay? But we ask, we can't answer, but we ask, is the universe, capital T, capital U, infinite in extent or not? And we don't know. All we know is it's bigger than the observable universe. Okay, but there could be a big cliff, 25 feet on the other side of the observable universe, and we don't know what's there. Okay.
Right up the
yeah, right.
So before I end the recording, and we'll I'll hang out here for a few more minutes. Ken is asking a great question, and this is kind of an interesting thing. In 2018, I think that's right. I took a trip to Italy, got to go to a few observatories, and they were talking about this concept of binary planetary system. So Ken asked a question, can Earth's moon be called a planet? Earth and moon would be like a binary planet pair.
Yeah. So that's a great question. So this again is a question about nomenclature, right? Is what should we call the moon? We have always called the moon a satellite of the Earth because it is smaller than the Earth. But the moon is unusual. If you look at the solar system, we'll keep Pluto out of this for the moment, right? Is if you look at all the other planets in the solar system that have moons, none of them have a moon that is as large as ours. Okay, and so the question is, what is normal for a moon? Right, and the moon's unusual size is largely a function of the mechanism by which we think it formed. The current best understanding of the formation of the moon is that a Mars-sized object hit the Earth early in its life. That object is called Theia, for those of you who go look this up, and that the two, when they collided, couldn't stay bound together, and the part that spun off was quite large, and it became the moon. Okay, so the question becomes, well, what does that make the moon, right? The moon is a piece of the Earth that spun off. It's smaller than the Earth, but is it another planet? I mean, because if it had broken off from the Earth and gone into its own orbit around the sun, we'd call it a planet, right? But you know, there are things that are large, like Ceres, which are not planets by our current nomenclature. But Ceres is big and round, just like the moon. So, you know, this is all about taxonomy, and taxonomy is hard. Okay, and so I think as an astronomer, the way I think about things like this is, well, I don't really care what you call it. The important thing is it exists, so there has to be a reason for it to exist. So can we figure that out? Because if we can figure that out, then we can answer the question of, is it common in the universe? Are there other places in the universe where the parent planet or the larger of the two is of similar size to the Earth and the companion is similar size to the moon? That's the interesting bit, because that's where all the physics and astrophysics is hiding.
Yeah, that's a good interest. I kind of wish Jerry was with us tonight, because I know we have this conversation a lot. So I'm going to end the recording part of this. I want to thank everyone for joining us tonight, and I want to wish you a happy holidays. Be sure to come down and check out the Nature Center during the day. They're going to be open every day, and of course the Second Turn thrift store, not open on Christmas or New Year's Day, but they're open on Fridays and Saturdays. So be sure to check them out. And once again, Shane, thank you so much for hanging out with us. I know there's a few staff people that have a few more questions for us. So if you can bear with us
for a little while,
for a few more minutes. I know it's 2 hours later your time. So, but thank you everyone for joining us tonight. We hope you have a wonderful holidays, and we look forward to seeing you at the observatory soon. And once again, thank you again. And hopefully, and it looks like second quarter of 2022, we're going to be doing more of these Zoom things, because it's the way of the world right now. So
the way the world is right now. So thanks everyone. It was great seeing you all. Thanks for all the great questions.
I'm going to go ahead and stop the recording here.